All right, good morning, everybody. How was your weekend? Actually, I didn't realize that the exam was last weekend. I was thinking it would be this coming weekend. So I think I mentioned that we will continue reviewing some things about Taylor polynomials this week. But yeah, I hope you did well in your exams. We will start grading it. I guess there are 4 FRQ questions for the exam. So we will grade your tests until Thursday. So hopefully over the weekend, it will be uploaded in CASA. So you will see your FRQ total score on Monday, probably, or at the earliest over the weekend. All right. So yeah, how was it, guys? You don't want to talk about it? Yeah, nobody.
It was really hard.
Oh, yeah, I
Very.
imagine because now you have 4 FRQ questions, and at least question 1 or question 17 has 2 parts already. So yeah, I understand why it could be that tiring. But let's see. Hopefully, you still did well. Okay, and then this would be the last full week of classes. So I just checked the academic calendar, and it seems that the last day of classes is on March 3. Oh, sorry, May 3. And you will have the final exam sometime the second week of May, if I'm not mistaken. Kindly check on that. But I'm thinking, what is the coverage for the final exam? Did Dr. Almus tell you what the coverage would be? Will it be cover to cover, or will it just be the remainder of the topics that were not included in any exam yet? Okay, you don't know yet, so maybe I'll check up on that so that we can schedule our remaining lab classes accordingly. So I look at your CASA calendar, and it seems that you were told to watch a video for the first 2 sections of Chapter 10, which is about polar coordinates. So have you guys had the time to watch the videos? It's about the introduction to a brand new type of coordinate system. So I guess we were just, or you were just, you have just, um, you had just been using the rectangular coordinates, but this time we will introduce you to a new one, which is called the polar coordinate system. So, okay, good, Herson. How about the others? Because I guess this morning in the lecture you started 10.3 and 10.4. So I'm thinking maybe I'll give you a couple of practice problems for sections 10.1 and 10.2. I mean, we'll discuss some of them. And if those are very easy for you, then I can also take a look at exercises from 10.3. Okay, you haven't finished 10.3 yet. That's good. So for today, let's try to do 10.1 and 10.2, which is basically introduction to polar coordinates. I'm not sure what 10.3 is. Is it about areas? Okay, but anyway, so okay, sure. So let's talk about 10.3. Let's defer it until Wednesday. So for today, let's talk about the basic of a polar coordinate system. So in the just a quick recap. So, and for the benefit also of those who haven't had a chance to look at the video yet, we're used to the rectangular coordinate system. So you have your x comma y, and a point in this space or in this two-dimensional space has 2 coordinates, right? We say it has x component and y component. The x component's going to be the horizontal, the value in the horizontal axis, while the component is the value on the vertical axis, right? So for every point on the two-dimensional space, there is a unique pair of coordinates x and y that represents that point, right? Now that is in contrast to polar coordinates, wherein we have what we call the polar axis. Okay, but oftentimes they also draw a vertical axis, though in the definition of the polar axis it is non-existence. It is non-existent. So the main reference here is this, which is the point here, which we call the pole. Okay, in the you can think of it as the equivalent of the origin in the rectangular coordinate. Sometimes we also call the pole as the origin for the polar coordinate system. Um, for a point in the polar space, say have a point here, a point P. This point P will also have a pair of coordinates. The coordinates would be r and theta. I guess I'll follow the conventions in the textbook. They use square brackets to denote polar coordinates and parentheses for the rectangular coordinates to remove confusion with them. Now, how do we find this r and theta component? Now, the r component is basically the distance of the point coming from the pole. So the pole is also the point of inference. You can think of it as well as the equivalent of the origin. So the r component is basically the distance coming from the pole towards towards the point. So you need to measure how long that distance is. While the theta component is basically the angle coming from the polar axis measured clockwise. So this would be your theta component. And this brings us to one important difference between the two coordinate systems. Now, for polar coordinate systems, for the polar coordinate system, a point can be represented by infinitely many polar coordinates or pair of polar coordinates. Because if this is theta, right, then you can take another revolution around the polar axis and you will have r comma theta plus r comma theta plus 2 pi. That is another representation for this certain point. You can take another complete revolution around the polar axis. You'll have r comma theta plus 4 pi. That will represent the same point r comma theta. So unlike rectangular coordinates, points in the polar coordinate system will have infinitely many representations. And it's not just playing with the theta component, but you can also play with the r component. Though I mentioned earlier that the r component represents the distance between the pole and the point, r can be negative, which is somewhat a little bit misleading because we said r is the distance between the pole and the point, but r can be negative. And what's the effect? Well, say if you have the point, let's give an example here. So let's plot the point. Let's plot the point 2 comma, say pi over 3. Okay. Oops. They should be square brackets. So oftentimes you also draw a vertical axis for the polar coordinates, and that's the line theta equals pi over 2. Okay. Now we need to draw. Usually I look at the angle pi over 3 first. So say this is pi over 3, which is about 60 degrees. Okay. That's pi over 3. Okay. And then now to find a point 2 comma pi over 3, I move 2 units coming from the pole. So if this is the pole, I travel the 2 units along the theta equals pi over 3 line. And say that's 2 units. So that means this would be my point. All right. So this is the point 2 comma pi over 3. And as I mentioned, this is the same as 2 comma 7 pi over 3, all right? Because 7 pi over 3 is just pi over 3 plus 2 pi, right? So that means I just traveled another 2 pi units and I'll get at the same point, right? So that's another representation for that single point. Now we can also do it this way. If I want a negative r, I can say, okay, this would be negative 2. But when plotting a polar point with a negative r component, you go into the uh, the opposite direction. So in order to get this same point with a negative r value, I will use the angle, which is supplementary to pi over 3. So that means if I have a negative angle here, I'll start at this point and then count negative 2 units. If I'll be counting negative 2 units, that will be 2 units backward. So this would be okay, negative 2 comma 4 pi over 3. That's the representation of the point 2 comma pi over 3 with the negative r value. Now, maybe it's easier to see it in reverse. So how do we find that, or how do we plot points with the negative r value? First, you look at the angle 4 pi over 3. Now, the angle 4 pi over 3 is this. Let me label it here. From here until here, that's 4 pi over 3 units, okay? Now, if r is positive, then I should have drawn the point somewhere here along the line theta equals 4 pi over 3. But since r is negative 2, instead of drawing it in this segment, at the segment theta equals 4 pi over 3, I will move 2 units backwards. So essentially drawing the line here, 2 units, that will bring me there. So you can get infinitely many polar representations for a single point by two ways. You can play with the angular component, which is the theta component. You can add or subtract any multiple of 2 pi, or you can change the r value from a positive one to a negative one, and you find the supplementary angle to the theta component. Okay. Now, of course, there is a nice relationship between the polar and the rectangular coordinates. So we can have, or we can define some conversion factors. But hold on, guys, let me pause a bit. All right, so here are the conversion factors. Okay, so if you know the Cartesian coordinates, so maybe let's start rectangular to polar. So you can find the r component to satisfy this equation. Okay, r squared equals x squared plus y squared. Again, you can have a negative value for r or a positive value for r, but this is the relationship between the two. And theta is the angle such that tangent theta equals y over x, right? So that's how you find the rectangular, the polar representation for a rectangular point x comma y. On the other hand, if you know the polar coordinates and you want to convert it into the rectangular coordinates, you will use the following relation. X equals r cosine theta and y is equal to r sine theta. So you can remember this easily by remembering that x is always associated with a cosine, y is always associated with a sine. And with this information over here, we can play with the relationship between the two coordinate systems. But just a quick caveat here, I don't want to write it as theta equals arctan of y over x, because in order to get the theta component, you should take note on which quadrant you are in. So if I write it as an arctan, remember arctans are just limited on the first and the fourth quadrants. So from negative pi over 2 to pi over 2. So you might be missing out the third and the fourth quadrant. So it is essential to know at what angle or at what quadrant your rectangular point lies in order to pick the theta correctly. All right. So let's look at some examples here before going to the next topic, which is about testing symmetries and the different graphs. So I have here in worksheet 22 some of the I copied the exercises from the textbook, sections 10.1 and 10.2. So let's try answering some of them. Okay, let's try, okay. Let's try the first instruction here is to, okay. Maybe I'll combine the instructions here. Plot the following polar points. Okay. Now I'll have problem number 2, but if you see some interesting problems in the worksheet, just let me know. Or if you already tried answering some of the quizzes or online assignments, just let me know, and then I can I can walk you through some of them, because I'm not familiar how advanced the problems in the quizzes are. So just let me know. Okay, let's try the first one. Let's plot -3, 0. Again, we use angular brackets for polar points, at least as per the textbook. So that's what I'm gonna use here. So -3, 0. So say this is my polar coordinates. So this is my polar axis. This is my pole. This is the polar axis. Okay. Now -3, 0. Now R value is negative, so I need to look at the angle 0. The angle 0 is here. This is theta equals 0. But since the R value is negative, I will not plot along the theta equals 0 axis, but rather I will plot it in the supplementary angle. So in this case, that would be pi, or 180 degrees. So -3 units along the supplementary angle will bring me from here 3 units until here. So this would be my point -3, 0. Okay. Let's try another one. Problem 4, -1/2, pi over 4. Again, I have a negative r here, so let's remember that. Now I look at theta equals pi over 4. Theta equals pi over 4 is somewhere here. That's 45 degrees. So that's theta equals pi over 4. But I will not plot along theta equals pi over 4 because my r value again is negative. So instead, I'll look for the supplementary angle to pi over 4, which is just the angle directly opposite pi over 4. That will bring us here at 5 pi over 4, and count half a unit along that angle. So half a unit, perhaps somewhere here. So let's put our point somewhere here. So let me just label them with arrows here. So this guy would be -1/2, pi over 4. And then lastly, let's try problem 6, which is 3, 5 pi over 6. Now I look for the angle 5 pi over 6. The angle 5 pi over 6 is in the second quadrant, right? So second quadrant, maybe perhaps somewhere here. Let's label that like that. Theta equals pi over 6, all right? 5 pi over 6. And then I'll count 3 units because r is positive. So I'll count along the exact angle, 3 units. So perhaps somewhere around here. So this is our point 3, 5 pi over 6. All right, any questions so far? All good? Especially for those who haven't watched the videos yet about this section. Yeah, I would like also to apologize. I'm gonna pause several times during the session because I have my allergies today. So yeah, I need to take some time to clear my nose out. But okay, I hope that's fine. So any questions so far? None? Everything's fine? Okay, let's go to the second section, which is second set of exercises, which is to convert the following to rectangular coordinates. Okay, let's try problem 8. So we have -1, comma 2 pi over 3. Since these are polar coordinates, we know that r would be negative and theta is 2 pi over 3. So we'll just use the conversion factors or the conversion formulas that we introduced earlier. Remember that the x component can be computed using the cosine function, right? Because x is always associated with cosine. The formula is x equals r cosine theta. Plug in those values. So r is -1 times cosine of 2 pi over 3. But what is cosine of 2 pi over 3? Cosine of 2 pi over 3 is... So if you draw the circle, so pi over 3 will have cosine equal to... Yeah, whenever evaluating trig functions, I always need to draw a unit circle. So this would be, I think it's 1/2. So if you go 2 pi over 3, that's going to be -1/2. Is that correct? Cosine of 2 pi over 3 is -1/2. Yeah, I should have prepared the unit circle with me. Yeah, 2 pi over 3, yeah, it's -1/2. So this would be the x component would be 1 over 2. Okay. And then the y component would be r sine theta. So that would be -1 times sine of 2 pi over 3. That's going to be -1. And sine of 2 pi over 3 is √3 over 2. So this would be -√3 over 2. So the Cartesian or the rectangular coordinate for this guy is 1/2 comma -√3 over 2. Okay, is that good? So this is purely mechanical, and I always think that the conversion from polar to rectangular is much easier because it's straightforward. Plug in the r value, plug in the theta value, right? And I don't see any big complication with this. So guys, do you have any questions for this? Or do you want another example? I can do another quick one just to familiarize you with the process. So let's try 3 comma -pi over 2. Okay. Now again, here r is +3. Theta is -pi over 2. So x is r cosine theta. So you'll have 3 times cosine of -pi over 2. But that's going to be 0. So x component is 0. And then y is equal to r sine theta. That's going to be 3 times sine of -pi over 2, which is -1. So I'll have 3 times -1. So this would be -3, right? One nice way to check if your answer is correct is to plot both points, because they are equivalent points. Then they should appear at exactly the same point in the two-dimensional space. So let's start. Let's see how they look like in the 2D space. So in in polar coordinates, we are given 3 comma negative pi over 2. The negative pi over 2 angle is somewhere here. Oops. So this is theta equals negative pi over 2, right? Because that's going to be negative pi over 2 units. And the R value here is positive 3. So I will count 3 units along that angular line. So the point will be somewhere here. That's 3 units away, right? Now, if you plot the point, the Cartesian point, we said it's 0, comma, negative 3 in Cartesian coordinates. So 0, negative 3, oh, we will have the same point here. So that means this is the same point being represented by 3, comma, negative pi over 2 and 0, comma, negative 3. So they will really coincide. It by its polar coordinates. All right, let's try another one. I think that's fine. Let's go to the next. The let's play this game in reverse. I mean, let's find the polar coordinates. Let me see. Let me just review what is the actual instruction there. 10.2, third section. We're told find all possible polar coordinates for each point. So let's find all polar representations. For the following points. Okay, so with emphasis on all, so we need to derive a general formula for all of the representations for the following Cartesian points in their in polar coordinates. So I'll try problem 14, which is the point 2 comma negative 2 in Cartesian coordinates. So basically what you can do first is before plotting it, maybe we can compute the R value, right? So we have the formula R squared equals X squared plus Y squared. So that means we'll have R squared equals 2 squared plus negative 2 squared. So that means we'll have 4 plus 4. So we'll have 8. So that means R is equal to plus or minus root 8 or plus or minus 2 root 2, right? So these are the two possible R values that we can use in representing the points in polar coordinates. Now, for theta, we know that theta or tangent of theta equals y over x. So that means that tangent theta should be equal to negative 2 over 2, right? But we need to make sure, we need to know at what quadrant does theta lie, okay? Now, because it's easy that tangent theta equals negative 1. If you will hit it up with an arctan, the answer would be negative pi over 4, right? Because that's the angle on the between negative pi over 2 and pi over 2. But we need to make sure we are on the right quadrant. All right, so let's plot the point 2 comma negative 2 in Cartesian. So we'll have 2 here, negative 2 here. Okay, we really are on the fourth quadrant. So quadrant 4. So we can say that theta could be equal to, well, 11 pi, not 11, but 7 pi over 4. Okay. Or you could also say it's theta equals negative pi over 4, right? Which is fine. If you hit it up with an arctan, this is the guy that you will get. But if it happened that the angle or the point is at the third quadrant, then using the arctan will be wrong because you will get negative pi over 4, sorry, in the second quadrant rather. So if the point is in the second quadrant, you use arctan, you will get theta equals negative pi over 4, but actually theta would be 3 pi over 4, right? So be careful with this conversion. Do not hit it up with an arctan unless you know exactly on which quadrant you are on. Okay, hopefully I'll have an example here when that will happen. Okay, yeah, I have one. Okay, so now we have one representation. So one representation would be the usual one, right? So we know that this angle is 7 pi over 4. So one representation for this would be r, the positive root, so 2 root 2, comma, 7 pi over 4. Okay, but that's just a single representation. Another representation with the negative r value. Okay, if you want a negative r value here, then all you need to do is instead of giving 7 pi over 4, you give the supplementary angle to it. So you can use this point here, which is theta equals 3 pi over 4. All right. So, and then, but here, since theta equals 3 pi over 4 will be here, in order to get at the same point, we need to draw the point backwards. That's why we have the negative sign in front of it. So here we'll have 3 pi over 4, which is another representation. So we can begin, actually, let's make it 2 representations for this angle, right? And then from these 2 representations, one with a positive r value and another with a negative r value, I can derive all other representations. So that means any polar representation for the point 2 comma negative 2 would be of the form, okay, we begin with 1, the one with the positive root. And then we said you can add or subtract any multiple of 2 pi, okay, at the angle, right? Because an addition or subtraction of a multiple of 2 pi will just require you to move another revolution around the unit circle. So here this would be valid as long as k is an integer, or we can use the negative root and then use the fundamental angle we found earlier and add to it a multiple of 2 pi. So again, k is an integer. So this would be all the representations. So hold on. So this would be all the representations for the Cartesian point 2 comma negative 2. All right. Any questions so far? You guys are very quiet today, even on the chat. So I can deduce from that that you haven't tried any quizzes regarding polar coordinates yet, which is fine. I know you had a lot of things going on over the weekend, but I hope this is making sense. Any questions so far? Yeah, I see Daryl. Though I haven't started grading it yet, but we're grading problem 17 today, which is about um, testing the series using, I guess it has 2 parts. For the first one, you can use either ratio or root test. For the other part, you can do limit comparison or direct comparison. So I don't have an idea yet. Oh, sure. Go ahead, Daryl.
Hello, Neil. So I took the test and I worked out my problems. I didn't realize until after the fact that I did not put my problem code for number 20. And
Uh-huh.
I also had a peer that did the same thing. So we emailed the professor, and they had said that the grading TA would try to find the code.
Yep, that's right.
That if they couldn't, they won't grade it.
Yeah.
So I was wondering if you might have any advice or rationale to offer on that.
Well, the thing, what I can advise you about is wait for the FRQ. If the grading TA found the test, then good for you. If he didn't find the actual question or he wasn't able to get the test code for that based on the given problem, so just let me know, and then I can trace it back and do it more carefully, because some TAs are very strict. They'll just give it one shot and they will quit because yeah, that's fine because you were told to write the test code. But yeah, if the grading TA won't find was not able to find it, just let me know and then I'll take a look at it. Okay.
Thank you so much, Neil. Sorry about
Right.
that.
No problem. Yeah. Uh, One possible drawback of that is that the grading TA might be grumpy at that point if it will take him a lot of time to find that specific problem. So yeah, he might be grumpy grading it, but yeah.
Yeah, I'm anticipating that too. They're gonna be harsh on me.
Right. But well, we understand. Most TAs understand that you are under a lot of pressure doing the exam. So yeah, we most of us let it fly and give our utmost patience to grading your problems. All right.
Thank you.
Okay. So about this, any questions, guys? None so far. Let me try another one. Or do you think these problems are very easy or these are very elementary? Because I don't want to start talking about problems from section 10.3 because you haven't finished it yet. Okay, let's try problem 18 then. Same instruction, let's find all polar representatives for the Cartesian point -2, comma 2 root 3. Okay. Now, again, finding the r value is easier because r squared equals x squared plus y squared. So this would be, or this will imply r squared is equal to -2 squared plus 2 root 3 squared. So this would be 4 plus 4 times 3. So this would be 16, right? So that means r could be plus or minus 4. So you need to be careful. We were asked to find all representations for this Cartesian point. So that includes a positive value for r and a negative value for r as well. That's why whenever I'm writing the conversion factors, I want to start with r squared equals x squared plus y squared instead of r equals root of x squared plus y squared. Because again, we allow r to have a negative value. Okay. Now to find theta, so we know that theta satisfies this. Okay, tangent theta equals y over x. So that gives us tangent theta equals 2 root 3 over -2, which is negative root 3. All right. But here we are on which quadrant? So if you plot the point, we have -2 comma 2 root 3. So x is -2, y is 2 root 3. So we are on the third quadrant. So hitting this up with an arctan will not give us the exact angle because remember arctans only give us angle from -pi/2 to pi/2. And this is clearly outside of that interval, right? So we need to be a little bit creative in finding that arctan value. So what I usually do is to imagine this. How do I get -√3/2? So this would be √3/2 all over 1/2. Because I know √3/2 and 1/2 come as a pair insofar as the unit circle is concerned, right? But we want the x component to be negative because we are on the second quadrant. The x component is negative there. All right. Now, when does this occur? So I'll think of what is the angle theta, wherein this is my sine and this is my cosine, right? So sine is positive √3/2 at let's see, let me think. It's positive √3/2. Oh, it's the other way around. I should have put the negative sign over here. Yeah, because the y, hold on. Oh, this is right. This should be negative because this is the x component. We are on the third quadrant, all right? Now, what is the angle whose sine is positive √3/2? It's gonna be 2 pi over 3, right? So this implies theta equals 2 pi over 3. Because 2 pi over 3 is the angle whose sine is positive √3/2 and whose cosine is negative 1/2. If those are the two values, then the tangent would be negative √3/2. Okay? Now, there's a big difference because, again, if I'll hit it up with an arctan, what that will give me is theta equals negative pi over 3, which is not what we wanted, right? Because we are on the second quadrant. Because theta should lie in quadrant number 2, right? So two representations, which you can call as our base representations for 2 comma or for negative 2 comma 2√3 are the following. So we have with a positive r value, we can use r equals 4, and we'll use the actual theta value. So that's 2 pi over 3, which is fine because when we draw the plot, we go at theta equals 2 pi over 3. So this is theta equals 2 pi over 3. And from here until there, that's going to be 4 units. Good. Now, on the other hand, if I want to use a negative 4 as my r value, I will not plot along, I will not use this particular theta, but I will use the supplementary theta. The supplementary theta is over here, which is what? It should be 5 pi over 3. Right? Okay. So these are our two representations for this value. Again, 5 pi over 3 is here. If you want to double check, try to plot this. Theta equals 5 pi over 3 somewhere here. But since r is negative 4, I will travel in the opposite direction instead and travel 4 units there. So I'll arrive at the same point. Okay. So with these two base representations, what are the other representations? So all polar representations of this point are of the form 4 comma 2 pi over 3 plus 2k pi, representing a multiple of 2 pi, or negative 4 comma 5 pi over 3 plus 2k pi for any integer k. Okay, so that's how you find all the polar representations for a certain polar point. Now let's try working using equations, right? So using the same conversion factors, we can write a polar equation into its Cartesian form or vice versa. So let's try, let's see. Okay, let's try some problems from this set. Oops. Right. Let's try, say, problem 28. Well, let's try with an easy one. Problem 27. Problem 27, write the following given equations in polar coordinates. So we start with x squared plus y squared equals 16. So we know that x squared plus y squared is basically r squared equals 16. Yeah, equals 16. So this is the polar equivalent for this point. So this is what? A circle of radius 4, centered at the origin. And so this guy will also be the circle of radius 4 centered at the origin in polar representation. So you can go further and say this is r equals plus or minus 4, all right? Or you can go further and say that this is just r equals 4. Why can we ignore the negative root? Because if you want to plot all points satisfying this, right? So r equals 4. If you look at r equals 4, you're just looking for all points on the polar plane whose distance from the pole is 4 units. So if I say from here until here, it's 4 units. So I'll be here. That's 4 units. From here until here is 4 units. Okay. And you see that if I collect all those points, I'll have a circle. But this doesn't look like a circle at all. So let me try again. Okay, there we go. That looks better. So if you have positive 4, then you will be able to collect the entire circle already. If you use r equals negative 4, then you will get the entire circle also. So you can ignore the negative root there. So you can either say it's r squared equals 16 or r equals 4. All right. Let's try a more complicated one. Let's try problem 20. I think it's 28. Let me see. Okay. It's x squared plus y minus 1 squared equals 9. The thing is, I guess the easiest way to write Cartesian equation into its polar equivalent is to use the fact that r squared equals x squared plus y squared whenever possible. I mean, I do not want to use r equals plus or minus root of x squared plus y squared in my equation. So I want to start with an x squared plus y squared first and go from there, because I don't want to complicate the form of the equation by using square roots all throughout my derivation. So here, what I can do is, of course, one way is to replace x by r cosine theta, plus you replace y by r sine theta, minus 1 quantity squared equals 9. This is in itself a polar equation, so you can stop here, or unless you're told specifically to simplify your answer. But I want a more elegant answer here. So what I'm going to do, instead of r cosine and then using r sine theta, I'm going to do it this way. I will do the expansion, x squared plus y squared minus 2y plus 1 equals 9. So I'll have x squared plus y squared minus 2y equals 8. All right. And then, oh, I have an x squared plus y squared over here, and that's equal to r squared. Minus 2, then I have a lonely y here, and y is r sine theta equals 8. So I can write it as r squared minus 2r sine theta equals 8, which looks nicer than the previous answer that I've shown you. But if you will simplify the first answer that I had, you will get this more elegant form for the equation as well. Okay, So basically, this represents a circle centered at 0, 1 with radius 9. This guy will also represent that. So this is the circle of radius 3 units centered at 0, -1. The Cartesian point 0, -1. Actually, you can further simplify this and say what? Actually, it won't look good when simplified because you'll have an r minus 2 sine theta equals 8. So you can divide both sides by either expression, but that won't look good. So I'll probably stop here and use this as my final representation. All right. Now it's already time, but please take some time answering some of the problems in section 10.1, specifically the conversions of polar to Cartesian equations. So you can play with this set of exercises and let me know on Wednesday if you had some difficulties with this. All right. Now, what I'll try to focus on Wednesday is here, which is basically sketching the polar curves, because there are lots of polar curves. They're what we call, of course, you have circles, you have also lines. The more interesting ones are the limaçons, the lemniscates, roses, or how does the textbook calls it? I think it is called petals. I usually call them roses. And then what are the other? Yeah, I think those are the different type of polar curves that we'll try to sketch, because sketching them is crucial in finding the area inside of those curves. So we'll talk about sketching polar curves next time, and hopefully on Friday start working on exercises 10.3 to 10.2. Right? Oh, sure. Problem 27. Here we go. All right. Do you have any questions about it, Sosa?
No, I just wanted to see what you did.
All right. Yeah. Okay, that's fine. So I guess that's pretty straightforward because I just replaced x squared plus y squared by r squared. That's in our conversions. The more challenging one was problem 28. There are several ways of writing it, so I want you guys to explore it on your own. Try to answer again some of the problems from the sections I highlighted in exercises 10.1. And let me know on Wednesday if you had some difficulties with them, but I'll focus on sketching polar graphs on Wednesday. All right, guys? Okay, so let's end here, and I'll see you again on Wednesday. Bye, guys.
Mr. Neil, just to remind you, I sent you a DM.
Oh, sure,
Can you
yeah.
please check that out?
Yeah, I'll take a look at it. All right.